Hello everyone, I am Mr. M. Vignesh. Welcome to this lecture on diodes. A diode is one of the most fundamental semiconductor devices used in electronics. It allows current to flow in only one direction and blocks it in the opposite direction. Diodes are used in mobile chargers, televisions, computers, LED lights and many other electronic devices. In this lecture we will understand the basic concepts of diodes, their operation, characteristics and practical applications. Let's begin. Topics to be covered. Before we start, let us look at today's topics. We will first understand the electrical properties of different materials. Then we will study semiconductors and the process of doping. Next we will learn why a diode is required and how a PN junction is formed. Finally we will discuss forward bias, reverse bias, diode characteristics, practical silicon diodes, special purpose diodes and some important applications. By the end of this lecture you will have a clear understanding of diode fundamentals. Electrical properties of solids. Before learning about diodes, we need to understand the electrical properties of different materials. Materials are mainly classified into conductor, semiconductor and insulators. Conductors such as copper and aluminum contain a large number of free electrons. These electrons move freely when a voltage is applied, producing electric current. Insulators such as rubber and polyethylene have electrons that are tightly bound to their bottoms. Therefore, they do not allow current to flow easily. Semiconductors have the properties that lie between conductors and insulators. Their conductivity can be controlled, making them suitable for electronic devices. Semiconductors. Now let us understand semiconductors. The most commonly used semiconductor materials are silicon and germanium. In a pure semiconductor, thermal energy breaks a few covalent bonds, creating free electrons. Whenever an electron leaves its bond, it creates an empty space called a hole. Electrons carry negative charge while holes behave as a positive charge carrier. Since only a few charge carriers are available at the room temperature, pure semiconductors conduct electricity poorly. This type of conducting is called as intrinsic conduction. Doping. To increase the conductivity of a semiconductor, we use the process called as doping. Doping means adding a very small amount of impurity atoms to pure silicon. If the impurity contributes extra electrons, the semiconductor becomes N-type. If the impurity creates extra holes, it becomes P-type. Both N-type and P-type semiconductor conduct electricity much better than pure semiconductor. This process is known as extrinsic conduction. Diagrams are shown in this picture for P-type and N-type semiconductor. P-type and N-type semiconductor. In an N-type semiconductor, electrons are available in large numbers. Therefore, electrons are called majority charge carriers. Holes are present in very small numbers and are called minority charge carriers. Similarly, in P-type semiconductor, holes are the majority charge carriers, where electrons are the minority charge carriers. Even after doping, the semiconductor remains electrically neutral because these positive and negative charges are balanced. Why do we need a diode? Let us understand why we need a diode. Many electronic circuits require current to flow in only one direction. For example, a mobile phone charge converts alternating current to direct current. Resistor can only limit current, it cannot control the direction of current flow. A diode solves this problem by allowing current to pass in one direction while blocking it in the opposite direction. This makes the diode an essential component in electronic circuits. Ideal diode. An ideal diode is a theoretical model. It behaves like a perfect switch. When it is forward bias, it offers zero resistance and allows current to flow freely. When it is reverse bias, it offers infinite resistance and complete blocking current. Although no practical diode behaves exactly like this, the ideal diode model helps us to understand the basic operation of a real diode. Ideal diode application as a half-wave rectifier. One of the most common applications of diode is rectification. Rectification is the process of converting alternating current into a direct current, AC to DC. The circuit shown here is called as half-wave rectifier. During positive half cycle of the AC input, the diode conducts current. During negative half cycle, the diode blocks current. As a result, only one half of the input waveform appears at the output. Transition to PN junction. So far, we have discussed the behavior of an ideal diode. However, in practice, no real diode is perfect. Real diodes are made using semiconductor materials. To understand how an actual diode works, we must first study the PN junction, which forms the heart of the every semiconductor diode. In the next section, we will see how joining P-type and N-type materials creates a PN junction and how this junction controls the flow of current. We will continue with this PN junction. Now let us understand how a PN junction is formed. A diode is created by joining a P-type semiconductor and N-type semiconductor. When these two materials come into contact, electrons from the N-type region move towards the P-type region. Similarly, holes from the P-type region move towards the N-type region. As these electrons and holes combine, they cancel each other near the junction. As a result, a region with a very few charge carriers is formed. The region is known as the depletion region or space charge region. The depletion region plays an important role in controlling the flow of current through the diode. In this slide, we will see the potential barrier. As electrons and holes diffuse across the junction, they have charged ions behind. This creates an electric field across the depletion region. The electric field produces a voltage called the potential barrier. The potential barrier opposes the movement of majority charge carriers across the junction. Without an external voltage, this barrier prevents current from flowing through the diode. Understanding the potential barrier is important because it explains why a diode doesn't conduct under normal conditions. Diffusion and drift currents. Even though the potential barrier blocks most charge carriers, two small currents still exist. The first is the diffusion current produced by majority charge carriers that have enough energy to cross the junction. The second is the drift current produced by the minority charge carriers moving under the influence of the electric field. In an isolated PN junction, these two currents are equal and opposite. Therefore, the net current through the diode is zero. This is the equilibrium condition of a PN junction. Then now let us see what happens when we apply an external voltage. When the positive terminal of the battery is connected to P-type region and negative terminal is connected to the N-type region, the diode is said to be forward biased. The applied voltage reduces the potential barrier. The depletion region becomes thinner. As a result, more electrons holes cross the junction. This causes large current to flow through the diode. Therefore, in forward bias, the diode behaves like a closed switch. Now we will consider the opposite case. When the positive terminal is connected to N-type region and negative terminal is connected to P-type region, the diode is reverse biased. The depletion region becomes wider. The potential barrier increases. Majority charge carriers cannot cross the junction. Only very small leakage current caused by minority charge carriers flows to the diode. This current is extremely small and is usually neglected. Therefore, the diode behaves like an open switch in reverse bias. So this slide shows the IV characteristics graph of a PN junction diode in forward bias and in reverse bias and then isolated junction. This slide shows the diode equation that is actually given by a Shockley diode given as an equation. This equation shows that diode current increases exponentially with the applied forward voltage. A small increase in forward voltage produces a large increase in the current. This is the diagram showing the behavior of the current with respect to the temperature. This slide shows the IV characteristics curve. The graph clearly shows the practical behavior of a diode under different potential conditions. Notice that current remains almost zero until the forward voltage reaches the cut-in voltage. In reverse bias, only a tiny leakage current flows until breakdown occurs. Real silicon diodes are not ideal, so we'll see what are practical silicon diode. A practical silicon diode requires approximately 0.7 volts before it starts conducting properly. This is called as forward voltage drop. And every diode has a maximum current rating and a breakdown voltage. These values depend on the design and application of the diode. When designing electronic circuits, engineers always select a diode with suitable voltage and current rating. So in the next part, we will cover the remaining topics. So thank you for watching this lecture.